This section will explain the concepts of urban resilience, and will discuss theoretical approaches to resilient cities. In this slide, an overall framework of the course content is presented. The concept of urban resilience and the resilience capacity of cities are introduced, followed by an examination of urban form typologies that enhance resilience and the morphological characteristics that contribute to risk reduction. In addition, the core principles of resilient urban forms are explained, and selected examples from Japan, Medellin, and Southeast Asia are used to evaluate how these approaches are applied in practice. Urban resilience and identify urban form typologies that enhance resilience. Understand the spatial logic behind risk-reducing morphologies. Explore global examples of resilient design patterns. Resilience is defined as the ability of individuals, communities, cities, institutions and societies to prevent, resist, absorb, adapt, respond to and recover from various risks in a positive, productive and effective manner without compromising the future. In terms of its relationship with the environment in which it is experienced, it varies as urban, ecological, social and economic resilience. Urban resilience refers to the ability of any urban system, together with its inhabitants, to adapt to possible shocks and stresses, maintain continuity, resist and recover from them while transforming into more sustainable urban systems. In other words, it is the capacity of individuals, communities, institutions, businesses and systems in a city to survive, adapt and grow despite any chronic stress and acute shocks they experience. The literature on the resilience of cities in the face of disasters, crises, changes and shocks offers a multidimensional theoretical framework. Approaches to the subject commonly focus on Holling's ecological resilience approach, Vale and Campanella's urban resilience approach and UN Habitat's holistic approach. Holling's ecological resilience approach, 1973, is one of the approaches that form the basis for studies on cities in ecological literature. It treats cities not as static structures but as dynamic, adaptable systems that simultaneously possess fragile and robust aspects, capable of reorganizing themselves in the face of change and possessing a capacity for transformation. It is a groundbreaking model that explains how ecological and later socio-ecological systems respond to shocks and changes and how they engage with life. According to Holling, resilience is the ability of an ecosystem or city to cope with disruption and change and maintain its basic functions in such situations without losing the relationships between its constituent elements. Although Holling's ecological resilience approach was initially conceived for ecological systems, the scope of the concept was later expanded to socio-ecological systems, SES. Socio-ecological resilience focuses on the following three characteristics of ecosystems and cities. 1. Absorption capacity, the ability to withstand damage or disturbance without losing basic functions. 2. Reorganization capacity, the ability to transition to a new state, equilibrium, and restructure itself after encountering a situation. 3. Adaptation and learning capacity, the ability to learn from past experiences and prepare for future changes. This approach requires cities not only to be resilient in the face of disasters and shocks, but also to be flexible after disruption, to recover quickly, and to develop the ability to adapt to future threats. Holling's concept of ecological resilience has led to a paradigm shift in urban planning and disaster management. It has therefore become a cornerstone of urban resilience literature and practice. Vale and Campanella's approach to urban resilience, 2005, brings a historical and multidimensional perspective to urban resilience. It assesses resilience through urban memory, cultural continuity and reconstruction processes, focusing not only on the robustness of physical infrastructure but also on social, cultural and institutional strength. According to this perspective, resilience is not merely about repairing physical damage but also encompasses the social, symbolic and political dimensions of the city. Following Holling's ecological resilience approach, this approach emphasizes the ability to preserve the integrity of the urban system. It also addresses the post-disaster recovery process through the physical and infrastructure dimension, the social and human dimension, and the political and symbolic dimension. According to Vale and Campanella, a city's resilience is determined not only by how robust its buildings are, but also by how strong a sense of shared belonging its citizens have and how fairly and effectively the political system can manage recovery. UN Habitat's approach is forward-looking and action-oriented, as well as holistic and multidimensional, with a focus on sustainable development, inclusiveness and risk reduction. According to UN Habitat, a resilient city is one that can withstand multiple shocks and stresses, natural disasters, climate change, economic crises, epidemics, social inequalities, etc., recover quickly from them, and positively transform towards sustainability by ensuring the continuity of essential urban services. UN Habitat views resilience not only as post-disaster recovery, but also as the city's ability to adapt and transform in response to future uncertainties. It addresses urban resilience as institutional, economic, social and environmental resilience using tools such as the City Resilience Profiling and Assessment Tool, CRPAT, developed to assess the vulnerabilities of cities. It presents a city's resilience as a multi-layered planning paradigm based on inclusive, adaptable, flexible and preventive principles. UN Habitat's approach is a global framework that demonstrates that urban resilience is not merely a technical issue but is also closely linked to governance, equity and sustainable development. Urban form theories will be explained under the headings Components of Urban Form and Urban Typologies and in the context of resilience. Theorists conducting city-based studies, such as Alexander, Calthorpe, Cullen, Hillier, Gell, and Lynch, emphasize density, morphology, diversity of use, and network structures when explaining the components of urban form and the structure of urban space. These components are core elements that determine the functioning, spatial structure, accessibility, perceptibility, social relations, and environmental performance of cities. Density refers to the population or structures located in a unit area. At the urban scale, land use decisions are an important component in terms of sustainability, accessibility, and urban quality of life. Morphology defines the physical form of cities, the physical order of the urban fabric, parcel structure, building typologies, settlement fabric, etc., and spatial organization. It determines accessibility, walkability, microclimate, street vitality, and the quality of public spaces in cities. Land use diversity refers to the spatial distribution of land use types, residential, commercial, industrial, etc. It increases pedestrian mobility in urban life, supports public transport, strengthens social interaction, and has indirect effects on urban heat islands and energy consumption. Network structures encompass transportation, communication, green infrastructure, and social interaction networks in the urban space. They generally refer to the spatial organization of transportation and accessibility networks, pedestrian, bicycle, public transport, etc. The connectivity of the network determines economic interaction, carbon emissions, and spatial resilience, primarily mobility. Urban form typologies that increase resilience are formed as a reflection of the search for the ideal city. While each typology is produced to solve the problems of its era, it has different effects on urban resilience indicators such as ecological permeability, post-disaster recovery, energy efficiency, and accessibility. The most resilient urban form in the face of disasters is one that embraces the principles of sustainable, inclusive, and integrated planning. Rather than a single geometric form, the characteristics of the most resilient forms are a modular, multi-centered structure with redundant infrastructure, integrated with green spaces and strong community ties. This means a city that reduces risks, can withstand damage, adapt quickly, and return to its former state, or even improve. Typologies that increase resilience are explained below. Grid form is a regular urban fabric consisting of streets, avenues, blocks, squares, parks, and other urban areas, with streets intersecting at right angles to each other, distributing traffic evenly. It is a strong typology in terms of resilience due to its high connectivity, flexibility, energy efficiency, high accessibility, and open structure for development. The radial, central, form is an urban fabric based on main axes, spreading from the center to the periphery with a hierarchical street structure. While its center-focused structure provides advantages for public transport systems, a single center structure can increase traffic load and carbon emissions due to excessive centralization. Furthermore, any negative event in the center can affect the entire system. It is effective as long as the center is strong, but carries the risk of fragility. Organic, irregular, traditional, Form is an urban fabric shaped by topography, historical development and parcel structure, consisting of unpredictable street networks. It is compatible with the natural terrain and advantageous in terms of microclimate. Although it has high social resilience, it lacks flexibility in terms of transport and accessibility in emergencies. Hybrid, mixed, form is an urban typology consisting of mixed settlement structures. Its multi-centered structure, transport diversity and adaptability make it one of the most balanced typologies in terms of urban resilience. It offers the advantages of distributed risk and flexibility. In this slide, grid, radial, organic, and hybrid urban form typologies are compared in terms of their strengths, weaknesses, and overall resilience levels. This comparison highlights how different urban forms perform under disaster risk conditions and indicates the contexts in which each typology may offer advantages in planning and design processes. Risk-reducing urban forms are urban typologies designed to minimize disaster risks and support rapid recovery after disasters, using planning and design principles to make cities more resilient to the destructive effects of natural and man-made disasters and to increase their recovery capacity. Urban forms and characteristic structures aimed at reducing disaster risks, green infrastructure and ecological forms that integrate natural processes into urban systems by avoiding buffer zones and hazardous areas and increasing permeable surfaces, forms of functional diversity and modularity that incorporate varying densities and mixed uses, utilize localized infrastructure and resources, and aim to reduce dependence on a single center and increase flexibility during disasters. Forms that prioritize transport and access networks, aiming to increase emergency response and evacuation capacity by considering sufficiently wide roads, redundant transport networks, and walkable urban forms, forms that ensure structural and spatial standards focused on increasing resilience at the building level through disaster assembly areas, open spaces, and fire-resistant settlements and materials. Basic principles of urban forms aimed at reducing disaster risks: low vulnerability, strong building stock, low-density risk areas, use of durable materials. High accessibility and connectivity, emergency routes, alternative routes, continuity of open spaces. Blue-green infrastructure integration, stream corridors, permeable surfaces and rain gardens that provide flood control. Modular and multi-core urban structure, distributed centers in a network structure instead of a single center system. Open and flexible public space network, evacuation assembly areas, fire separation gaps, post-disaster logistics centers. Avoidance of natural hazard zones, restrictions on construction in fault lines, flood valleys and landslide areas. Continuity in energy and transport infrastructure, off-grid alternatives and micro-energy systems. The principles of resilient urban forms will be explained under three headings. Modularity and redundancy in layout. Modularity is defined as the division of urban systems, networks, infrastructure, neighborhoods, into small, independent and standardized components, while redundancy refers to the existence of multiple independent paths and resources for performing critical functions. They preserve system integrity and prevent the spread of disruption in the event of a crisis, natural disaster or infrastructure failure. Grid-type road networks prevent any congestion from halting all traffic, while local energy production provides examples of infrastructure redundancy against central grid failure. Furthermore, multi-purpose buildings, flexible units, that can serve different purposes as needed are examples of applications that enable service provision. These applications are factors that enable rapid response and recovery, allow a large part of the infrastructure system to continue operating, and eliminate any single point of failure that may arise in the system. Integration with natural systems, e.g., water, vegetation. The design of urban infrastructure, roads, buildings, drainage, to mimic or work in harmony with the region's ecological processes, water cycle, biodiversity, climate regulation. They focus on rainwater management, the biodiversity of green spaces, and reducing the urban heat island effect. They buffer and protect cities from external influences. They mitigate the effects of natural disasters, floods, droughts, extreme heat, integrate ecosystem services, clean air, water filtration, into the city, and improve quality of life. Bioengineered solutions, permeable pavements, and rain gardens are key applications for managing rainwater. Green roofs and vertical gardens, which provide vegetation cover, help reduce surface runoff. Creating large urban wooded areas helps lower temperatures and mitigate the urban heat island effect. These are important application examples at the urban scale. These applications are important factors in reducing flood risk, saving energy, and promoting biodiversity and health. Flexibility for adaptation and change over time. The design of urban infrastructure, roads, buildings, drainage, to mimic or work in harmony with the region's ecological processes, water cycle, biodiversity, climate regulation. They focus on rainwater management, the biodiversity of green spaces, and reducing the urban heat island effect. They buffer and protect cities from external influences. They mitigate the effects of natural disasters, floods, droughts, extreme heat, integrate ecosystem services, clean air, water filtration, into the city, and improve quality of life. Examples of spatial planning based on capacity that can adapt to multiple scenarios, along with transport infrastructure that allows for flexibility in building use and enables conversion or different uses, are important applications. These applications will enable buildings and infrastructure to become long-term investments, gaining the ability to adapt to changes after disasters while maintaining economic efficiency. Global typologies possess distinct characteristics that offer solutions specific to geographical location, climatic challenges, and natural disaster risks. The polder-based flood-adaptive settlements in the Netherlands, Japan's compact, modular forms with seismic zoning, Colombia-Medellin's slope-sensitive stair-linked housing clusters, and Southeast Asia's stilt-based housing with canal integration are important examples on a global scale. It is the most important water management and settlement planning model that the country has used for centuries. As approximately 26% of the Netherlands' land is below sea level, the model has been established on reclaimed land that is below or just above sea level. Today, in order to adapt to rising sea levels due to the climate crisis, water management, water levels are controlled by a system of dikes, embankments, pumps, and drainage channels. Flexible architecture. Housing is designed according to flood risk, with floating houses or structures built to withstand rising water levels. Fundamentally based on protection and adaptation against flooding, the model focuses on keeping water under control and designing settlements to cope with water. It describes three fundamental characteristics of urban planning and building design in areas of high earthquake risk in Japan. These are: compact city form. Due to limited land capacity, cities have a high density but orderly and compact structure. Small plots, vertical development, rail-oriented settlements, walkable distances, and neighborhoods accommodating different land uses are key features, while a compact urban fabric reduces traffic, promotes efficient land use, and facilitates evacuation during disasters. Modular architecture and flexibility. Modular construction is frequently used to enhance earthquake performance and shorten construction time. Key features include the assembly of factory-produced modules on site, ease of repair and renewal, the design of the load-bearing system to dissipate seismic energy, and the prevalence of lightweight steel or timber frame systems. Planning according to seismic zones. As Japan is located in one of the most active earthquake belts, urban planning and building regulations are approached based on the principle of documenting the seismic hazard of the land. Key features include the preparation of risk maps based on the ground, building restrictions near fault lines, measures taken on coasts against tsunami risk, refuge hills and vertical evacuation points, and the requirement for seismic isolation or damping systems in multi-story buildings. This resilient urban design application consists of slope-sensitive housing clusters connected by staircases or transport systems, implemented over the last 20 years through social transformation strategies in irregular settlement areas spread across steep slopes around the city of Medellin, Colombia. The dwellings are constructed in a stepped and terraced manner to adapt to the natural slope of the hillsides. Wide public staircases, including escalators, and cable car lines connect the settlement to the city center and urban services. Slope stabilization, drainage systems and retaining structures have been built to reduce the risk of landslides. It strengthens social resilience and improves the quality of life on sloping terrain by increasing social and economic accessibility. This is an urban resilience approach developed in response to floods, monsoon rains, floods and tidal changes commonly seen in Southeast Asian countries such as Vietnam, Thailand, Cambodia, Indonesia and Myanmar. The stilt houses and canal settlements seen in these regions are the product of a water-adaptive living culture. Homes are built above ground level to protect against rising water levels, and canals are integrated into the urban fabric not only for transportation but also for effective drainage and managing excess water. Houses are built on stilts above ground level to protect them from fluctuating water levels. Canals are integrated into the urban fabric not only for transportation purposes but also for effective drainage and managing excess water. This provides structural protection against high water levels, floods, and tidal changes, while canals serve as a functional part of urban life. Urban typology influences resilience, mobility, and access. Typologies must respond to hazard, culture, and landscape. Form is a foundation for climate-responsive communities.